932. Good morning. I understand that I'm teaching here. There is no one in the class, but still I'm not going to take attendance. So I will deal with column clamped at one end and free at the other. So we deal with the buckling of such a column. That means that column is like this. So boundary conditions are here at 0, x equals 0, w equals 0, and first derivative equals 0. Okay, at x equals 0. Here, then, bending moment equals 0. That is one thing. And then what we call it, effective shear force equals 0. I will write down this expression of effective shear force. So that is 16.1. So we know what shear force is. And of course, here we should talk, our displacement is V, 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 and here is V, and here is V. Now, so I will write down column, clamped at one end, and free at the other, and subjected to concentrated load P compression. So I will depict again this beam, this column. That is L, so x equals 0. Here x equals L. So at x equals 0, we have V equals 0 and V prime equals 0. At x equals L, bending moment, of course, is 0. And that means EI V double prime is 0. And then shear force. We will leave here for one word space. Shear force equals 0. Now with shear force, let us look how the deformation proceeds. That is this beam, and we will show the whole beam. And then there is this force P. So de facto, what is a shear force? Shear force is a force that is shear to the cross-section. That means that that is this force. Force is in this direction, and we call it Vy or V effective. So what we know about shear force is that shear force equals EI V double prime, which is a bending moment, first derivative. Okay? But here, because there is this load projects in this direction. So that is this load. So this load projects in this direction. So therefore, actually, we should multiply by cosine of this angle. So angle, say alpha. So then we have V effective equals EI V double prime, first derivative, and then plus P, and then, okay, this cosine of this angle. This angle we can calculate equals V prime. So we have boundary condition. Boundary condition, second boundary condition is given by EI V double prime prime plus P V prime equals 0. So we have this one and this boundary condition at the end. I will leave it for a moment so that you could write down. I will zoom so that you could see the whole page. So let us satisfy boundary conditions. 16.2. So we have V of x equals, let me see what expression, the general expressions that we have is. I will tell you also the page number. Yes, so that is A1 sine K Z plus A2, or in this case, X. A2 cosine K X plus A3X plus A4. And that is page 15.5. So when I satisfy boundary condition at x equals 0, then I get, let me look at this, 16.2b. So V of x equals A1 sine kx plus A2 cosine kx plus A3x plus A4. When I substitute x equals 0, will be A1 sine k of 0 plus A2 cosine k 0 plus A3 0 plus A4 equals 0. So this is 0. This is 0 also. So I get A2 plus, this is 1, plus A4 equals 0. Then we get, that is one condition. Let us go back. Yeah, A2 plus A4 equals 0. Then we have the first derivative, V prime of x equals A1k cosine kx plus A2 minus A2k sine kx plus A3. So V prime at 0 equals a1k cosine k times 0 minus a2k sine k times 0 plus a3, that must be 0. This is 1, this is gone, so we get a1k plus a3 equals 0. Yes. So then we have second derivative equals 0. Okay, so this one at L. So second derivative will be, so that is first derivative. Second derivative of x equals minus a1k squared sine kx. I'm calculating from here. Then kx. Then minus a2k squared cosinus kx. And this is gone. So v prime at L equals 0 means minus a1k squared sine kl minus a2k squared cosine kl equals 0, which is written here. So page 16, 2a. And then third derivative. Third derivative, v third derivative of x equals, here I'm differentiating, minus a1k cubed cosine kx and plus a2k cubed sine kx. That is a third derivative. So let me write it. Let us leave it here. So then we have EI, V third derivative plus PV first derivative at x equals L equals 0. That is effective shear force. So then we get, look, this expression. EI, and this one, minus k cubed a1 cosine kl, plus a2k cubed sine kl, plus p times first derivative. First derivative is given here. K a1 cosine kl minus a2k sine kl plus a3. So everything is correct. Okay, because P over, so here, there is P and there is EI. I divide everything by EI, divide by everything EI. So I get instead of P here then K squared. So then last equation transforms this one. Look please, there is K squared, but there is K squared and K will be K cubed. But there is here plus sign with cosine kl and minus sign. So these two terms will cancel. Okay, this term and this term will cancel each other. So then here, I have k squared times k will be k cubed, a2k cubed sine kl, and there is this one. So this term and this term will cancel each other. So, but this term stays. So we have k squared a3 equals 0. So then from equations we get a1 equals a3 equals 0, a2 equals minus a4. So then from these equations we get cosine kl equals 0. What is the solution of this cosine kl equals 0? That is, so kl must equal to an odd number times pi. So odd number can be written 2n minus 1. Okay, odd number. So will be, so KL equals 2n minus 1 over 2 pi, n equals 1, 2, etc. For example, n equals 1 will be 2 times 1, which is 2, minus 1 is 1. So cosine equals indeed for pi over 2. Then 2, second next root will be 2 times 2 is 4, 4 minus 1, 3, 3 pi over 2. So then from here, because it's KL equals, K equals P over EI, we are getting P equals pi squared 2n minus 1 squared EI over 4L squared. So there are many buckling loads. Now, A1 equals A3, A2 equals minus A4. So let me write it down. Expression was V of x equals A1 sine kx plus A2 cosine kx plus A3x plus A4. A1 is 0. A3 is 0. But A4 equals minus A2. So will be A2 cosine, that is a buckling mode. Cosine kx. Then instead of A4, I will write minus A2. Or maybe I will write down, instead of A2, I will write minus A4. So minus A4. And then it is plus A4. So we get A4, 1 minus cosine kx. Or that equals A4, 1 minus, now k, I should substitute k from here. Will be cosine 2n minus 1 pi over Lx. So that is what is written here. So that is a mode shape. So the smallest value is n equals 1. N equals 1, we get buckling load. P classical or P critical, we used P critical, equals pi squared EI over 4L squared. Okay, so that gives us an expression for buckling load, which is 1/4 of buckling load for simply supported column. Okay. Okay, these materials, these typed pages are coming from my lecture notes. That is here, 16-2C, if you want. A first course in buckling of structure, especially dedicated only to buckling. I started it long time ago in past century, and this material is not yet finished. But some pages I was able to share with you. Okay, so that is 16.2, 16.3. So we will consider now problems that are simpler than what we considered until now. Simplest stability problems. Question is, why should I consider first columns, which is more difficult topic, and only now consider simplest possible cases when column is considered to be rigid, absolutely rigid? I will explain you later, just on the second page. So here this column is absolutely rigid, and at x equals 0, it is connected with something that is called torsional spring. Now, what is a torsional spring? Torsional spring is a spring where there is a connection between moment and angle. And like this, moment is proportional to the angle. So moment is proportional to the angle. So that is this way. That means that whatever angle will be created is proportional to the moment that will be applied. Okay? That is a torsional spring. Now, if you remember, our buckling experiment was like this. We are putting some force here, then we give a kick to the system. Then we take out this kick that is like random wind, for example, loading. Then this beam comes back to the original condition. Then we increase the load. And again we give a kick. We take out this kick and beam again comes to the original position. There will be some time when I will give the kick, when I increase the load sufficiently. And this load will be some critical value. Then this beam does not come back to the original condition. Okay, so I'm depicting this beam in buckled state. Buckled state. So it buckled, so there is some theta here. There is naturally the moment acting, that is a free body diagram. And that is a critical value of the load, and displacement I'm denoting it as delta. Okay? Now I'm taking some of the moments with respect to this point O, or this is a point O. And look, this is a positive direction. This load gives me negative contribution. Minus P times delta. Here bending moment is positive, and it is theta times K theta. So I call it K theta. So K theta is at stiffness of torsional spring. So what happens is as follows. Look, please. We said 16.3b. Moment is proportional to theta. Okay? Now, that means that when moment is increasing, so theta is increasing. Question. How to get equality? So this is a qualitative description. Question, how to get equality? Here. Or how to get quantitative description? So then we have some coefficient. Moment should equal some coefficient times theta. So this coefficient is called K theta. Okay? Stiffness. And can be measured. So if we apply some moment, say 100 Newton times meter, and measure appropriate theta, angle that it creates. Okay, so I will call it theta 1. Then this then this k theta equals 100 Newton over meter divided by theta 1. So that is how we measure the stiffness. Just apply certain moment, check what angle system rotated, and ratio will be this stiffness. So that is experimental evaluation of the torsional stiffness. So this torsional stiffness we know, so minus P times delta, and then plus theta times k theta. Now how much is delta? That is this theta value. Okay? So naturally this is nothing else but sine, this L, that is length. L times sine theta. But for small values of theta, so that is this delta equals L times sine theta. But for small theta, we know from calculus that sine theta is S theta, approximated as theta. So then we get minus P L sine theta, but it is L times theta, plus theta k theta equals 0. Now we can take out the theta. And what is left here is minus PL plus k theta equals 0. Now, we can have either theta equals 0 or minus PL plus k theta equals 0. This is not possible. Why? Because this depicts the theta not 0. That is a buckling. When buckling occurs, this is theta is not 0. So theta is not 0. See the picture. That depicts column at buckling. So we should have written here P critical because I depicted this, that was a buckling situation. So here is P critical, and here is P critical, and P critical equals K theta divided by L. So buckling load equals the stiffness coefficient divided by length. Any questions? If you have any questions, please submit them. Via Canvas or email, and I will answer sending it to all. Okay, by Canvas. Send me any question and I will answer questions that you have. I will answer via Canvas. So what happens here, actually? 16.5. So we can depict, we would like to see the diagram. Load, and that is like a displacement or rotational angle. So load equals, everywhere until we reach this critical value, displacement is 0. Theta is 0, so that is where we are. Now at this value, P critical, then displacement is not 0. We don't know how much is the displacement. We don't know in this linear theory. How much is theta? We just know it is not 0. Okay, so that is the situation. Everywhere this is 0, and for every P, displacement is 0. So, pay attention, that is a nonlinear behavior. There is load, but there is 0 displacement. But at some load, suddenly, system like wakes up, gets, so to say, wakes up from this deep sleep and buckles. Okay, now we can ask the following question. At which value of k theta, P critical in absolutely rigid beam, here, equals the buckling load of the flexible beam? Okay, then pay attention. P critical equals k theta over L, and that is clamped free. This beam was clamped free. Buckling load we just derived, pi square EI over 4L squared. So then k theta we find equals pi squared EI over 4L. This is why we studied simpler problems later, otherwise we would have forgotten these simple problems. So idea is to engage you with thinking process. I think, therefore I am René Descartes, if you remember. Okay, any questions here? If not, we will continue. So we can only say that 16.6, rigid body resembles or might resemble the flexible body but only in first buckling load. Okay? We can establish only connection with first buckling load. In flexible body, the displacement is, this looks like this. That is P, that is V. So then here we have P critical 1, which equals pi square EI over 4L squared. And then expression, general expression is P critical equals 2n minus 1 squared pi squared EI. So 2n minus 1 L squared. So P critical 2 equals 2. 4 minus 1 is 3, so that is 9 pi square EI 4L squared. So that is 9 times bigger. So that is somewhere here. Okay? 9 pi square EI over 4L squared. So the picture then here is like this. Here it is 0, displacement is 0. V is 0, but here at this load, V is not 0. And this load also, V is not 0. So only this part of the picture can be reproduced by absolutely rigid bar, not the whole picture. Any questions? So actually here there is a third load, fourth load, etc. Depends on the kicks, what kind of kicks the system anticipates. Now there is also something that is called translational spring. The word is not very informative because it has nothing to do with translation, means translating from one language to another. That is displacement spring. Means that here load is proportional to the displacement. Okay? So that is T. So that displacement, so if I have such a spring, displacement is proportional to the load, or F equals K translational U. Okay, and that is this F equals K translational U, that is this picture. Okay, imagine that we have here translational spring and length equals L. Okay, then pay attention, that is a buckled position. That is 0, so that there is this load, and then spring load will be K translational X. That is this displacement. So I'm again take some of the moments. Okay, naturally there is this load here, etc., and the load here, but if I take the moment with respect to this point, all these loads give me 0 moment. Some of the moments with respect to O equals 0. So then load will be K translational X, and approximately this is length, okay, because this is a small displacement. X is very small, it is much smaller than length. And this P critical then is multiplied by X. Okay, X can be taken out. So what is left is K translational L minus P critical equals 0. So here again, X is not 0 because we have buckling. So then this is P critical equals K translational L. Okay. So pay attention. For translational spring, P critical is directly proportional to length. Here, for torsional spring, P critical is inversely proportional to length. Any questions? Okay, if there are no questions, we will consider some example. I took this example from some book, not our book. A 2.5 meter pivot ended means simple support. Air-dried Douglas fir column, so that is a material. Has a 50 by 100 millimeter rectangular cross section. Determines, okay, we will slenderness ratio, then Euler buckling load, yeah, you know what, before we proceed with this example, I would like to summarize the results that we have for beams. Summarize, so 16.8. Summary, column buckling. So what are the results that we obtained? Okay, for simply supported column, we got P critical equals 1 times pi squared EI over L squared. For clamped free column, we today obtained P critical equals 1/4 times pi squared EI over L squared. That is simply supported, SS, simply supported at both ends. Simply supported here, simply supported there. Clamped here, free there. 1/4. Here, P critical equals 205 pi approximately, pi square EI over L square, or approximately is 1 divided by half. Okay? Pi square EI over L square. That is clamped, simply supported. And here, clamped, we obtained, here factor is 4, pi square EI over L square. Okay, first thing is, one conclusion. Pi is an uninvited guest. Okay, pi, we did not talk about pi, we don't have a circular cross-section necessarily, but pi appeared in this analysis by itself. That is, if you remember Romeo and Juliet story, they meet because Romeo comes uninvited to Juliet's party. So pi is an uninvited guest. Second, general form of these equations is the same. P critical equals pi squared EI. Then there is L squared, but then there is some factor and L squared. Here I would like to discuss one topic. Yeah. And that is this topic. Okay, 16.8. Maybe I will put like this. 16.9. If you remember, so I will start from the other side. I asked the question. I asked, what value of P critical would you anticipate? For clamped, simply supported column. And one student said approximately 2 pi square EI over L square. Why 2? My question was, why 2? We could anticipate some average. Average would be, look, in clamped beam it is 4. In simply supported it is 1. So one could anticipate P average will be 1 plus 4 divided by 2 pi square EI over L square, which is 2.5 pi square EI over L square. So which shows that such an anticipation would be wrong. Such an anticipation would be wrong. But student was right. In her anticipation. So that is not a question, that is a statement. And indeed, there are something that is arithmetic average, A1, so there are two numbers, A1 and A2. Then arithmetic average will be A1 plus A2 divided by 2. But there is also geometric average, which is square root A1 times A2. So students, her anticipation was a correct geometric average approximation. Which is, look, 1 times 4 and square root pi square EI over L square, which is 2 pi square EI over L square. So it is not exactly, the answer is not exactly this. So that is first part, that is the second part. It's not exactly that, it is 2.05, but still this is a, I think, nice discussion. So there is this KL. Now I want, that is 16.8, 16.9, yes, 16.10. We want to be able to write formulas for P critical for any boundary condition in the form similar to that of simply supported column. So that is simply supported column, that is an expression. Similar form will be not to write L, but some effective length, LE. This LE then equals K times L. Effective length factor. L effective equals K times L. That is, this K is some coefficient as described on page, I think, 16.8. Yes, 16.8. Okay, now we would like to hear new notion, critical stress. So what is the value of the stress? That is a question. What is the value of the stress during buckling? So sigma critical equals P critical divided by area. A is a cross-sectional area. So that is this, so for simply supported case will be, or for general case, pi squared EI, KL squared. So now there is this I divided by A. That is a moment of inertia, that is A. That is area of the cross section. Yes. So let us continue with this. So there is this I divided by A. So first of all, let us make some observations. That for simply supported or pinned ends, pinned means simply supported, 1611. And that is pinned ends in the book. That is our book. Means simply supported. So K, big K equals 1. So L effective equals L. Now, for clamped free, then pay attention. Actually, we can consider that clamped free beam is half of the simply supported beam of length 2L. Okay? So clamped free column as simply supported column of length 2L, which is effective length. Then that formula is like simply supported. Okay, here for clamped end. So there are some, that is a buckling mode. So we can find the distance actually between points of inflection. And the distance between these points is half L. So that means that the length, as it were, of clamped beam is half length, and then beam is simply supported here. Therefore, buckling load will be 4 times bigger. And for the simply supported and clamped, the effective length is approximately 0.7, because below we have 0.7 times 0.7 will be 0.5. So 0.5 below gives me 2 up. Okay? So that is this P critical. And look, please, then this can be written, details in next page. Not here, that is he went too fast. Okay, so this is correct. That is pi square EI, that is KL square, and I have to divide by A. 1612. Maybe I will wait here, you will write down, make notes, because otherwise you have to both listen. After the lecture, I will scan this material and put on Canvas for your convenience. Please write down. So, okay, so we have I has a dimension of meter in force power. Area has a dimension of meter squared. So I over A will be meter in force power divided by meter squared equals meter squared. So we can denote it as something squared. And this something has a dimension r, has a dimension of meter. It is called radius of inertia. There is moment of inertia, this is radius of inertia. Okay, then sigma critical equals pi squared EI, then I over A, is it right? So it will be this R squared. Okay? And divided by KL squared. Because this guy is squared and this guy is squared, we can put this down here. We will get pi squared E, KL over R squared. Okay? So this is called effective slenderness ratio. And just slenderness ratio, just, not effective. Slenderness ratio equals, in Greek there is n, equals L divided by R, and is denoted usually as lambda. But we will be not using this notation because book does not use this notation, and I don't want to introduce additional letters because there is also effective slenderness ratio, etc. So that means length divided by areas, some compactness ratio. Oh, divided is a ratio, or area some compactness. So the formula is written like this. Yeah, as it is seen here. You see KL over R. Details on next page, details on 1612. That is here. And now we can proceed with example. Yeah, then it is not 16.8, but 16.13. A 2.5 meter pivot-ended air-dried Douglas fir column has 50 to 100 millimeter rectangular cross-section. Determine slenderness ratio. Okay, now we know what slenderness ratio is. Euler buckling load. The ratio of the axial stress under the action of the buckling load. Okay, so once I calculate the load, I should find the axial stress. So by dividing this load by the area. Then I would like to have the ratio of this stress to the elastic strength of the material, or yield stress. I would like to know how small or how big my buckling stress is in comparison with yield stress. Then also maximum load that column can support with factor of safety of 3.5. Okay, I already told you that factor of safety is for safety of the structure and the engineer okay? I will just write here King Hammurabi. So length equals 2.5 meters or 2,500 millimeters. Moment of inertia, this is the rectangular cross-section. BH cubed divided by 12. So A equals BH. So we calculate how much is radius of inertia. Okay, so that is radius of inertia. Square root I over A. That is BH cubed over 12 divided by BH, that is A. B and B are canceling each other. We get H cubed divided by H will be H squared. Square root of H squared is H. So 12 equals 4 times 3. Square root of 4 is 2. Square root of 3 is staying here. So radius of inertia equals H divided by 2 square root of 3. Any questions here? Now, wait a minute. Radius of gyration, 16, 14. So, this is, as I said, radius of inertia, R. Or radius of gyration. Now, pay attention. Maybe before that, maybe 16, 15, 16, 14. When we say Euler buckling load, that equals P critical equals pi square EI over L squared. If, of course, if cross-section is a circle, then I, moment of inertia, with respect to any axis is a constant quantity. But if the area equals like this, rectangle, so that is a simply supported. And this is also simple support. And there is this load P. And here there is load P. So there are possibilities of moment of inertia with respect to this axis or with respect to this axis. So let us say 1, and then there is possibility with respect to this 2. Then we have 2 buckling loads. P critical 1 equals pi square EI over L squared E1 with respect to axis 1. Or P critical 2, which equals pi square EI2 L squared. And that is axis 2. Which one is smaller? Naturally, pay attention. If we have such kicks, then system will buckle by load this. If I have such kicks, then system will buckle by this load. But we are not planning the kicks. Kicks come from outside environment. So therefore, we should protect system from any kicks. So therefore, P critical, we say, is minimum of P critical 1 and P critical 2. And naturally, smaller moment of inertia is associated with 1. Because, look please, this is, look, so imagine this is, we had this. So in this case, imagine that is 50 and that is 100. So I1 will be I1 100 times 50 cubed divided by 12. And I2 will be 50 times 100 cubed divided by 12. Which one is smaller? This is smaller, of course, because I'm taking in cube. So smallest in cube will be this. So I1 is smaller than I2. Despite the fact that here this factor is 100 and here it's 50, but it's only 2 times. Here, however, I am multiplying 3 times 100. Okay? So that is 2 times bigger than this, so it will be 8, but there is factor, so it's 4 times bigger. There is 8, but there is factor 2. So when we say we mean, okay, I will write it down, I minimum, and that is pi square EI1 over L squared. So that is 1614. Yeah, that's 1615. Radius of inertia, we wrote, minimum radius of inertia. Centroid axis parallel to longer side. So therefore, B equals 100. So we have to take centroidal axis parallel to longer side. B equals 100, H equals 50. R equals H, 2 square root of 3. So H equals 50, 2 square root of 3. So that equals 50 divided by 2 divided by 1.69 or something will be 14.434 millimeters. Slenderness ratio, L over R equals 2,500 divided by 14,434 equals 173. So slenderness ratio is non-dimensional quantity. It is indeed called ratio. Okay. Now, from the end of the book, of this book, we can find also the expressions for modulus of elasticity for air-dry Douglas fir, which equals 13 gigapascals. So we can find critical load. Critical load equals pi square E EA over L over R. Let's define this formula. Yes, that is a critical load. EA. So it will be pi squared 13, 10 to the power 9. Now A, 0.05 in meters, and that is 0.1, divided by 173 squared, will be 21.385, 10 to the power 3 newtons, or 21.4 kilonewtons. I'm giving examples as always. Why? Because this is lectures, but examples are incorporated in these lectures. So now I'm like your teaching assistant. Okay, axial stress. Sigma critical equals P critical divided by A. So 21.385, 10 to the power 3 newtons. divided by 0.05 times 0.1, that is an area, equals 4.277, 10 in power 6 Newton over meter squared, or 4.277 megapascals. That is a stress at buckling. At buckling. Okay? Second, 1616. The elastic strength of air-dried Douglas sphere is found to be, that is 44 megapascals. So that is the yield stress of this material. Thus the stress ratio is sigma critical divided by sigma y is 4.277 megapascals divided by 44 megapascals. It's 0.0972, so it's 9.72%. This demonstrates that buckling can occur at stresses well below the elastic limit of a material for sufficiently slender count. Okay, so you cannot say, come on, I will deal with strengths only. Not enough to deal with strengths only. So here we will write 1617. Not enough to deal with strengths only. Buckling is important consideration. The maximum load that the column can support with factor of safety 2.5 will be P critical divided by 2.5. 21,385 divided by 2.5 equals 855 kilonewtons. If we did not consider buckling, we would have obtained, this is approximately 9.72%, we would have said P maximum can be 85 kilonewtons. Approximately 85, 10 times more, because this is 9.72%, which is about 1/10. Okay, this strengthens us in the following. Okay, here we did not consider, so there are failure modes. Failure modes. So the strengths, then stiffness. We did not consider this in this problem. In this problem, we did not deal with it. Then C, buckling. I would like to address also another issue. Now I'm teaching here, which means in Fleming Hall 401. It is possible, if I will inform you, maybe I will transfer myself to WebEx. If university will not allow us professors to come to the university, then I will have to teach from home. Then I will transfer myself to WebEx, but I will inform you. Now at this moment, this will be on Canvas, and you can access it whenever you want. I prefer this to WebEx because WebEx only allows you to attend while you listen to me, but then it is not available later. This, because it will be on Canvas, is available always during the semester. So you can access this lecture, repeat, come back. I thought that that was more convenient for you students. Thank you very much. Have a good day. Please email me any questions if you have. 9, 8, 7, 6, 5, 4, 3, 2. Yeah. Yeah, this is important. Otherwise, sometimes Oh, I did not talk about this. You know what? Maybe I will put it here. No, there is no place to put it. No, that I will throw it away. You see? I got it in Japan. That is shell buckling phenomenon. And this I got because I wrote to Tuborg and they sent me empty. We buckled this. Okay, you can take this and I will take this. Okay. See? Oh.